One of the very common way of representing a data set is using a matrix. Let's say how to represent it. As you might already know, a matrix is basically like a table, right? Suppose if my data set D is collection of xi, yi, I going from 1 to n. Let's say xi belongs to Rd, and let's say yi belongs to, let's say, Setosa virginica versicolor. Okay, let's say this representation we saw a while ago. Now let's put the same data in a matrix form. Okay, there are again two ways of representing it as a data matrix. I'll pick one. I'll also show you the other way of representing. So imagine if this is my data matrix, and let's assume, so what does this mean? This means that my xi is a d-dimensional vector, right? Which means I have d features. What does this mean? This means I have d features, right? I can write my features as columns of my matrix, f1, f2, f3, so on and so forth, fd, right? And I have n data points, right? I have first data point, second data point, third data point, so on and so forth, n data points. So this matrix is typically written as capital X, which is n cross d. Each row here, so the ith row here is nothing but your xi transpose, right? Here I'm representing each data point. As a row. Why did I write a transpose here? Because if I just wrote xi, the default xi is always a column vector. So xi transpose becomes a row vector, right? So if xi is a column vector, right? Xi transpose, which means swapping, which means basically converting your rows to columns and columns to rows, is a row vector, right? Now, given this, I'm representing xi transpose is now a row vector of d-dimensional space. So each row here corresponds to one data point. Each column corresponds to one feature. So if I have fj here, this is my jth feature, right? This is one way of representing, and each column represents a feature or a variable. This is one way of representing it. There is also exactly similar way of representing where, let me show it to you, where my x could be represented as this, where each row represents my features, f1, f2, f3, so on, fj, so on and so forth, fd. Okay, and each of my data points could be represented as column vectors, I, so on and so forth, n. So this is a d cross n matrix, and each of my points, my ith point xi is here. It's a column vector. This is, in this case, each column represents a data point, and each row represents a feature or a variable. So in this case, your features, your f1 could have been petal length, your f2 could have been petal width, your f3 could have been sepal length, your f4 could have been sepal width, right? So these are two representations, and remember this new x that I have written is nothing but transpose of this. If I just swap rows with columns with rows, you'll get this matrix. Okay, both of them are valid. In lot of research papers, you typically find this. Let me agree to that, because this falls naturally, right? Xi is a column vector by default. So they just stack up all the column vectors to make a matrix like this. When I studied and during my experience, I have used this format more. As long as somebody tells you what each column and each row is, it's okay. So I'll stick to this representation where each row is a data point and each column is a feature, right? This looks more like a table. So for example, I prefer this because it looks more like a table. There is no right or wrong approach as long as you specify what you're doing. So I like that approach because I can think of it like a table. I can think of my data as a table where each row, so this could be my sepal length, my sepal width, right? Petal length and petal width. My four features, my f1, my f2, my f3, my f3 and my f4. And each of these could be my flowers. My first flower, what is it? Sepal length, sepal width, petal length, petal width. My second flower, so on and so forth. So this is the first format that I explained to you, this format, right? Where each of my data, and it looks very similar to typical tabular representation of data, right? This is how you tabulate data, right? Each row is typically a flower or a data point, and each column is a feature. So I prefer to use this notation where each row is a data point, but a lot of research papers prefer to use this. It's perfectly okay to use any of them, but we will stick to this because I'm just more used to it, and it feels more natural, especially when you're tabulating data, right? So there is one more question. Okay, you explained how to represent your x, but what about y? Of course, I can represent y as a column vector here, right? As vector y. What is the length of the y? So this is a column vector, right? Which means it has n rows and one column. And the ith row, so this is my first row, second row, so on, my ith row, so on, so forth, nth row, because for each data point I have a yi, which says whether the flower is setosa, virginica, or versicolor. So here I'll have my yi corresponding to my xi row. This is important. Corresponding to my xi row, I'll have my yi. Okay, this is how we can represent data, where xi can be written as a matrix, where xi's can be all xi's can be concatenated or clubbed together to form a matrix like this, where each row is a data point, each column is a feature, and my y could be just one column of data, where yi corresponding to each xi there is a yi which represents what is the class label, right? And this is what we'll stick to. We'll use this extensively. We'll use this matrix x. We'll use this is matrix x, right? We'll use this matrix extensively in the next few lectures.